Hi, welcome to this video. In this video, I'm going to tell you something about my Stone Marten Repellent project, in which I made a Stone Marten Repellent with a power save mode. And this repellent is programmed with the YAL programming language. So what will the contents of this video? First, why I created this project. Then something about a commercial version, so a version that I purchased. The specification of this commercial version, but also some measurements that I did. Then I will explain my new design and also what the specifications are and the measurements that I did on this design. I will explain the software, how it works, something about the housing, a short video that demonstrates the device in action, and at the end of this video you can find some references. So about this project. I think I have a Stone Marten around my house, so I purchased a Stone Marten Repellent. It was battery powered and that was required because I don't have any power close to it, but the batteries did not last very long. So I performed some measurements to understand what was going on. Then I decided to build one myself, which uses less power. And I added a solar panel because I don't want to change the batteries all the time. So I'm using a solar panel and rechargeable batteries. I will also be reusing the cabinet. So this commercial version is this one. And if you open it up and you look at the back, you see the battery compartment with the 4 AA batteries. And inside you find one PCB. And this device is also capable of charging rechargeable batteries, and it has a piezo tweeter. So the specification of this device, it uses a frequency range between 15 kHz and 55 kHz. It's ultrasonic. And it starts at 15 kHz and then it increases to 55 kHz. So there's a sweep tone. And it does this a random number of times, somewhere between 3 and 7. And then it repeats this pattern every 2 minutes. And the reason for the changes in the tones and the repetitions is because the Stone Marten can get used to one pattern and then the device would not be effective anymore. And it uses the piezo tweeter. And the housing is water resistant. There are also some LEDs for generating light flashes, but you can switch those off. Then I did some measurements because the batteries did not last so long. So I did a measurement at the 6 volts, so 4 AA batteries. And I saw that the power LED is continuously on and it consumes 2.4 milliamps even when the device is idle. And when the device is active, it consumes around 10 milliamps, and that is without the flashing LEDs. I also measured the signal on the piezo tweeter and it was only 2.3 volt peak to peak. And that surprised me because the supply voltage is 6 volts. And you also see that the curve, the slope is not very steep in this signal. So the output is not very high. So I decided to make a new design. And it is built around a PIC Microcontroller, the 16F15313. But I'm also using the 74HC14 as an output buffer to give higher output on the piezo tweeter. I did not use any flashing LEDs, but I am using rechargeable batteries and a relatively large solar panel. And the reason for that is my device is not did not receive, let's say, direct sunlight, but is more in the shade. So I need a larger solar panel. So it's 11 by 11 centimeters, and at 7 volts it can offer 120 milliamps. The device will have an auto power save mode. And there is an option for night mode. That means you can enable the device so that it only operates at night and not during the day, because Stone Martens are most of the time active during the night. The LED that's on the device will indicate when an activity starts, but it will also indicate the operating mode where it's running for. I will explain that later. So this is the design. So if you start at the left, you see the connection for the solar panel, and then there's a voltage divider by R5 and R6, which is used to measure the voltage of the solar panel. And with the jumper GB1 you can enable the night mode. The solar panel is connected to the batteries via the Schottky diode D1. And the heart is formed by the PIC microcontroller, which controls the LED, but also has a voltage divider to measure the battery voltage. And on the right you find the 74HC14, the output buffer that drives the tweeter. And there's a pull-up resistor R4, and that's required because when the device is inactive, I'm switching the pin RA5 to input, which pulls up the signal and then means that the output is always low, the output of the 74HC14. And this is the board that I created. The active components are on one side of the board and the passive components are on the other side, and the reason for that is that otherwise it would not fit in the housing. So the specification. This device supports a frequency range between 20 kHz and 50 kHz. Now why 20? Because 15 kHz can be heard by my daughter, and that's very annoying. And a frequency above 50 kHz does not generate much output on the piezo tweeter. So the start tone is random. It starts at 20 kHz or at 50, so not always at 20 kHz. And it also uses a different sweep speed instead of only one. And it does this a random number of times, somewhere between 3 and 7 times. This cycle repeats after 2 minutes, at least in normal operation mode, or after 4 minutes when it's in power save mode. It also uses the piezo tweeter. And I also measured what the solar panel does, but in direct sunlight the solar panel supplies 150 mA charging current, which was much more than I expected, by the way. And the LED will blink when it starts, but it will also show in which mode it starts. In normal mode it starts with 3 blinks, in power save with 2 blinks, and in power low with 1 blink. But in power low mode no audio will be produced. So new measurements. They were done at 5 volts because I'm using 4 AA rechargeable batteries, so there's more or less 5 volts. When inactive, the device consumes only 25 microamps. And when active, it consumes around 50 milliamps. The signal on the piezo tweeter is 5 volt peak, so which is higher, much higher than in the purchase device. And here you can see the signal. But the signal is measured when the tweeter is connected to the output of the PIC. And you can see the curve is not very steep in the yellow line. And the blue line is the voltage that I measured over a resistor which was in series with a loudspeaker, a resistor of 10 ohm. And as you can see, it's more a peak than that is continuous consuming any power. Then I did the same measurement at the 74HC14, and then as you can see, the signal is much steeper. But also, if you look at the blue line, it seems that it's the same as the left picture, but that's not true, because on the right picture the voltage per division is 2 volts, and on the left it's only 500 millivolts. So the output is much higher when using the 74HC14. So the software. For the tone generation, I'm using the numeric controlled oscillator. That's why I have chosen for this PIC. And the sweep tone is created by running a timer. And in the interrupt, I'm increasing or decreasing the frequency each time. So this interrupt routine runs at 2 kHz or 4, because I have 2 speeds. So if you take one sweep from 50 to 20 or 20 to 50 kHz, it takes about 15 seconds, and at 4 kHz it takes about 7.5 seconds. I'm also measuring the battery voltage using the analog to digital converter. When the battery voltage is lower than 4.4 volts, so 1.1 per battery, it goes into power save mode. When the battery voltage is lower than that, so lower than 3.6 volts, it goes into low power mode. And I'm also measuring the solar panel voltage with the ADC. And the device will only be active when the solar panel voltage is lower than 2 volt. And if you remember the schematic diagram, if you don't install the jumper, the signal is pulled down to ground, so it will be active during the day and during the night. And the microcontroller goes to sleep when it's inactive, and then it consumes 25 microamps. And it wakes up from sleep mode by using the watchdog timer. So something about the housing. I'm using the housing of the original device because I couldn't use it anyway. This housing is water resistant, which is very nice. I'm also reusing the piezo tweeter. And in the new design, as you saw the board in the previous slides, it matches the sizes of the original board. And as I said, the active components are mounted at the top and the other components, the passive ones, are at the back. Then I made a plastic construction for the solar panel and I glued it on top of the housing. And on top of that, I made a plastic cover to protect the solar panel from rain. So this is what the board looks like inside of the housing. And this is the final design. You see it's a very large solar panel compared to the size of the housing. And this is another view. Okay, in the following video I'm going to make the ultrasonic sound visible because you can't hear it. And for that I'm using an ultrasonic receiver of 40 kHz and an oscilloscope. But this receiver has a resonance frequency at 40 kHz, so the sensitivity is only sensitive at 40 kHz and not so sensitive above or below that frequency. So you will only see a part of the whole spectrum of 20 kHz to 40, only the 40 kHz signal is seen. So I made two recordings that show the same signal, but the second recording uses a little bit a different angle, and then you can see also the LED blinking 3 times before it starts producing a tone. And also when you start, this was also in the original version, you can hear some clicking from the piezo tweeter. That will be the pulse that you saw on the oscilloscope. If you want to know more about this project, you can find it on my Github account. And if you want to know more about YAL and the YAL programming language, you can visit the YAL website. If you have questions on YAL, there's a very good YALib tutorial that you can download, or you can post your question in the YAList Google group. If you find bugs or you have specific requests, you can visit the YALib Google group. And all YAL sources, including the source of the compiler, can also be found on Github. I hope you liked this video, and thanks for watching.